Hey everyone, and welcome to another Explainer. Today we're unpacking one of the most baffling, exciting, and honestly truly revolutionary mysteries in the entire history of physics. I mean, it's a puzzle that fundamentally broke our understanding of the universe and forced scientists to completely rewrite the rulebook of reality. We're looking at the photoelectric effect.
Okay, let's dive right into this. Have you ever actually stopped to think about how weird light is? Just imagine you're shining a flashlight at a solid piece of metal. It seems completely harmless, right? It just lights up the surface. But underneath, on a microscopic level, that beam of light is somehow physically knocking particles right out of the metal. How is that even possible? How can something as seemingly weightless and intangible as a beam of light literally physically push something out of its way?
Section 1. The Great Physics Mystery. When the old rules broke down.
So picture this. We're placing ourselves right at the end of the 1800s. The greatest minds in classical physics thought they had the universe pretty much all figured out. But then they hit a total wall in the laboratory. The math just stopped working. And this phenomenon causing all the trouble was the photoelectric effect. By definition, it's the emission of electrons from a metal surface when light falls on it. And when these electrons get kicked out, we call them photoelectrons. You can kind of think of these electrons as tiny prisoners trapped inside a metallic jail cell. Under the right conditions, shining a light on that metal provides the exact key they need to escape. But the conditions for their escape, they made absolutely zero sense to classical physicists.
Because here's the baffling failure of those old rules. Under classical physics, light was just a continuous wave. So logic tells you that if you make the wave bigger, brighter and more intense, it should carry more energy, right? But scientists found that if you took a massive blinding spotlight of low-frequency light, like a bright red light, and blasted the metal with it, absolutely nothing happened. The prisoners stayed exactly where they were. Yet if you took a tiny, super faint beam of high-frequency light, boom, it instantly freed the electrons. I mean, no delay at all. It literally didn't matter how blindingly bright that low-frequency light was. It failed every single time.
Section 2. Einstein's Radical Solution. The Birth of the Photon in 1905.
So the whole scientific world is completely stuck. That is, until a young, relatively unknown patent clerk named Albert Einstein steps up to be the ultimate detective. And to solve this impossible puzzle, he realized he couldn't just tweak the old rules. Actually, scratch that. He had to completely throw them out and rewrite reality. He proposed we had to stop viewing light as just this smooth, continuous wave. Instead, he said light actually behaves like a stream of tiny, discrete packets of energy. And he called these little energy packets photons.
And Einstein didn't just throw out a cool concept, he brought the math to back it up. He gave us this incredibly elegant equation, E equals hf. Now the E is simply the energy of a single photon packet. The h is Planck's constant, that's just a fixed number in physics. But the F? That is the star of the show here. The F stands for the frequency of the light. So what this really means is that each tiny photon packet carries a very specific amount of energy, and that energy is dictated entirely by its frequency, not by how bright or intense the overall beam of light happens to be.
Which brings us to a massively important rule of the quantum universe. One photon transfers its energy to exactly one electron. It's a strict one-to-one interaction. Think of it like a vending machine. Let's say a snack costs exactly $1. You can't buy it by pouring in 100 separate pennies one at a time if the machine only accepts dollar coins, right? That bright, low-frequency spotlight, that's like throwing thousands of pennies at the machine. None of them work. But a single high-frequency photon is exactly like inserting the perfect single dollar coin. If that single photon's energy is high enough, the transaction clears and the electron escapes.
Section 3. Mechanics of the escape. The rules of the quantum game.
All right, now that we know who the main players are, let's look at exactly how they pull off this heist. We're going to transition into the precise mathematical mechanics of how these photons actually pull off the electron jailbreak. First up, we've got the threshold frequency. It's exactly what it sounds like. It's the bare minimum frequency needed to eject electrons. Remember how a photon's energy depends on its frequency? Well, this threshold is the absolute minimum frequency a photon must have to even attempt the job. If the incoming light is below this frequency, the photon simply doesn't have the punch to knock the electron out of its orbit.
So the crucial point here is understanding what that threshold actually represents inside the metal itself. It represents the work function, which is symbolized by the Greek letter phi. This is the minimum energy required to remove an electron from a metal. See, different metals have different microscopic structures, so they hold on to their electrons with varying strengths. The work function is the exact price, or basically the energy toll, that the photon must pay just to break the electron free from the metal's grip.
And what's really brilliant about Einstein's complete photoelectric equation is how it cleanly breaks the whole transaction down into a simple ledger. The incoming photon brings in its total energy, right? That's HF. The very first thing it has to do is pay the toll, the work function, phi, just to get the electron out. And whatever energy is left over after paying that toll becomes Ke, the kinetic energy of the emitted electron, which basically dictates exactly how fast the electron flies away.
And this perfectly clears up the whole mystery from earlier. It clearly contrasts the two different ways we can change the experiment. If we increase the intensity, meaning we just make the light brighter, assuming we're already above that minimum threshold, we're simply sending in more photons. More photons means more one-to-one collisions, which just pops out a higher quantity of electrons. But if we increase the frequency of the light, we are packing way more energy into every single photon. The toll to escape the metal stays exactly the same, so all that extra energy turns into kinetic energy, making those electrons fly out so much faster.
Section 4. Everyday Quantum Technology. The photoelectric effect in your life.
Now you might be thinking, this is just a bunch of 100-year-old textbook math. But no, this is the hidden engine behind the modern world. You interact with this exact quantum phenomenon every single day. When sunlight hits the solar panels on a roof, that's the photoelectric effect knocking electrons loose to create an electrical current. It's inside the photodiodes in your electronics. You know when you walk up to a grocery store and the automatic doors just magically slide open for you? A light beam is hitting a sensor, constantly knocking electrons loose. When your body breaks that beam, the flow of electrons stops, and the door's computer knows, hey, open up. It's literally everywhere.
Section 5. A quantum legacy. How one equation changed everything. So we've gone from a baffling lab experiment to opening grocery store doors, but the historical impact of this goes so much further. Let's look at how this built a legacy that completely reshaped human understanding. Step 1. Einstein unequivocally proved the particle nature of light, finally putting an end to centuries of scientific debate. Step 2. By showing that energy exists in these discrete little packets, he provided undeniably strong evidence for the newly born field of quantum theory. And Step 3. This brilliant, totally out-of-the-box deduction is exactly what earned Albert Einstein his Nobel Prize in Physics.
So if there's one core takeaway you remember from our explainer today, let it be this brilliantly simple truth right at the heart of the mystery. Light can eject electrons from metals because it behaves as particles called photons. It's just such an elegant, beautiful sentence that totally summarizes the crazy mechanics of the quantum universe.
But before we wrap up, I really want to leave you with this thought. Einstein proved that light, something we had always assumed was just a continuous wave, is actually a particle too. It has a completely dual nature. So as you go about your day today, I want you to wonder, if something as basic as light is both a wave and a particle, what else in our universe is secretly living a double life? Thanks for joining me on this explainer, and definitely keep questioning the reality around you.